Right, okay, folks. So I'm gonna start by introducing rate curves. This is the second video on the introduction to chemical kinetics, and I want to talk about rate curves. And let's look at this red and blue reactant reacting to give this purple product. Now, you already know that particles must collide. They must collide with the right energy, called activation energy, and they must collide at the right orientation. We already know that. And you should also know that the concentration of reactants will decrease and products will increase over time. We know that. Okay. Now let's look at the blue and red reactants, and let's pretend they're in solution. So all this white represents water. Okay. And they have to collide and they will produce that purple product. Okay. Now I'm going to start the clock, and you can see that the blue and red is decreasing and the purple is increasing as time goes on. Okay. And eventually all of the reactant will have changed into product, and you can see the reaction finished here in 40 seconds. Okay. Now I could represent that reaction, I could represent that change graphically like this. Okay. So the purple product is increasing with time, and you can see it levels off at 40 seconds because the reaction is over, and the rate curve will continue like this. Whereas the blue or red will decrease at an equal rate to the increase of the purple, because you could see in the equation, you could see way back here that one red reacts with one blue to give one purple, and therefore if I just come back now to the rate curve, you can see that for every purple produced, a red or blue is lost. So this curve is a mirror image of that curve there, and you can see that the change in purple over time is equal to, we have the negative sign here, is equal to the change in blue, which is equal to the change in red. So all that ought to make sense at this point here. This is, again, a bit more detail about rate curves. You can see that the gradient is getting less steep as time goes on. In other words, the reaction rate is decreasing. And we can see in the first minute here, we produced X amount of product. In the second minute, we produced Y amount of product. So the reaction is getting slower as time goes on. And we say average rate in the first minute because the actual rate is changing in that minute. And in the second minute, the rate is changing. It's actually getting less and less steep. So the reaction rate is decreasing as it happens. Okay? And showing you again here, you can have the amount of reactant decreasing with time. And again, the curve gets less and less steep as time goes on until the reaction is over. Okay. Now I've written why does the reaction rate decrease with time, and it's because the concentration of the reactants is decreasing with time. So the chance of a collision between the red and the blue particles, in our earlier case, is getting less with time, and therefore the rate is going to decrease. Now I've got here another rate curve in red, but you can see this here, this tangent I've drawn to the initial part of the curve is called the initial rate, and that's quite important in chemistry, the initial rate. This, on the other hand, is a tangent taken to that point there, and it's called the instantaneous rate at that moment. And of course, the rate is 0 there, okay? So this gradient here, this amount of product divided by that amount of time, that gives the initial rate of reaction. And coming back to this one, again, you can see that if I draw tangents, the reaction rate is decreasing, so the tangent is giving a less steep gradient as time has gone on. This is quite an important graph too, because the rate's decreasing with time, but I can get something called average rate if I divide the maximum amount of product, maximum concentration of product that was produced, divided by the time taken to reach that maximum. I get something called the average rate. it would be it would be the slope of this line if I went straight from there to there. Okay, there's an exam question here. This is the amount of oxygen being produced from hydrogen peroxide, I think it is, and you can see that the reaction gave a maximum of 60 cm of gas, and it took 80 seconds to get there. So this is how the average rate is calculated there. Okay. Again, hydrogen peroxide reaction here. It's the concentration of hydrogen peroxide is decreasing as the amount of oxygen is increasing, because that's the product. I'm going to ask you now what these three lines represent. So have a little think about that. You might want to pause the video. Well, the blue is the initial rate of reaction, when the reaction was the fastest there at the beginning. The red one represents the instantaneous rate right at that point there, right at 300 seconds. Instantaneous rate, where we've drawn a tangent there. And the dotted line represents the average rate up to 600 seconds, because it's going to continue, but the experimenter is able to get an average rate from 0 time to 600 seconds. Okay, and this is what's happened here. The hydrogen peroxide is producing oxygen, and you could collect that and measure its volume, or you could measure the concentration of this as time goes on, and you can see obviously the concentration is falling with time. Okay, the rate of the reaction can be expressed this way. It needs a negative sign because the concentration is actually falling, and once again we've got a similar graph there, and we've got some actual figures on there, so you could do some calculations. And this is the data in tabular form, which is probably not as useful, but you can see that these blue numbers represent intervals of 400 seconds. There we are, there's 400 in there, 400 between there and there, 400 between there and there, and so on. And this is the change in the concentration during that 400-second period. So if you subtract this number from this number, you get this number. That's the change. Divide by 400 and you get this rate. And you can see that the rate is falling as time goes on. The amount of peroxide that's decreasing in that 400-second period. Okay. So again, just reminding you, the concentration of reactants falls and the product rises. Now look at the red here. The red is changing into blue, and you can see that for every one red, there was one blue produced. So as the red goes down, the blue goes up at the same rate, and they are mirror images of each other. So these numbers here, these quantities are numerically equal. They just got different signs, that's all. So if that was 6 moles per minute decrease, that would be 6 moles per minute increase. They have to be, because the equation said that. The rate of consumption of the reactant is equal to the rate of formation of the product. Now take a close look at this. It's a bit confusing for some students, this, because they see that 2 there and they see a half there and they think, what's going on here? Well, you can see that for every mole of hydrogen consumed, there's a mole of iodine consumed. So these two numbers, these two quantities, are obviously numerically equal, aren't they? Right? But you can see that for every mole of hydrogen consumed, there are 2 moles of HI produced. So that means the rate of disappearance of this, or this, is going to be half the rate of appearance of HI. Okay, again, the rate of disappearance of this is going to be half the rate of appearance of this. And I've written it here, look. The rate of disappearance of hydrogen, or iodine, is half the rate of disappearance of HI, of appearance of HI. So that ought to make sense there. And you can see that the curves are not mirror images this time. You can see that the rate of decrease of hydrogen is actually going to be half. If you work it out, it should be half the rate of increase of HI. You can see from the equation there. Here's another example. Again, looks a bit confusing because there's no number there. The coefficient is 1, and yet I've put a 2 there. And that's because the rate of disappearance of this is equal to the rate of appearance of that. That makes sense because it's 2 to 2. And I've written it there. If it's 2 to 2, then it's 1 to 1, isn't it? So the rate of disappearance of that is equal to the rate of appearance of that. But you can see that this here is decreasing. It's getting less, decreasing at twice the rate that that's appearing. Okay, so in other words, the rate of disappearance of this or appearance of that is twice the rate of appearance of oxygen. So now hopefully that too makes sense. And it's therefore you can see it's important that you have to specify which reactant or product you're talking about when you measure rate, because if you're talking about this and you've got X moles per minute appearing, this will be 2X per moles disappearing. So you need to be very careful how you describe the rate. Okay. Now here's a complicated one here. You can see the ratio is 1 to 2 to half, or if you prefer, 2 to 4 to 1. And there's a little trick you can do here to get the equivalence, as we say. If you invert these coefficients, you get a half, a quarter, and 1. And now you have the equivalent rate expressions, because you can see that the rate of appearance of this should be half the rate of disappearance of that. Let's see if that's true now. Here we go. The rate of appearance of oxygen is half the rate of disappearance of that. That now makes sense. And if we relate these two, if we have a look at these two, you can see the rate of appearance of that should be a quarter of the rate of appearance of that. Let's look. The rate of appearance of oxygen is a quarter of the rate of appearance of that. So hopefully that now makes sense. If you put the data in tabular form, I've put here the concentration of N2O5 falling and NO2 rising and O2 rising with time. And I've picked this 500-second interval. Let's look here. In that 500-second interval, we've gone from 0.02 and we have decreased to 0.0086. If you then subtract this from this, here we are, you get this much. That's how much it's fallen. Now you can see the NO2, look at the ratio here. You can see that the NO2 should rise twice as much of that. And indeed, here we go, 2 times this gives us the 0.0228. So we went from nothing, there we are, these are experimental figures, so it's not going to be perfect, but you can see it's risen by twice the amount that's fallen, okay? And the oxygen, you can see, ought to be a quarter of this, or a half of that. So in the same period here, we've gone from 0 to 0.0057, and you can see that this value here is going to be a quarter of that, and it's going to be a half of that, okay? So hopefully these tabular forms of data make sense as well, okay? Now if you put that into a rate curve, you can see the curves are not going to be mirror images or anything like that. You can see the ratio is 2 to 4 to 2, and if I take this 100-second period, if the NO2 has gone up by 0.0037 moles, then you can see that the N2O5 there, that will have gone down by half as much, and you can see that's about half, isn't it, right? So that figure is about half that figure. And you can see that the oxygen, that will have gone, that would have risen by a quarter of the amount that's risen. So here's the NO2, and that is about a quarter of that, isn't it? Okay? So you can see how these numbers relate to each other simply by looking at the equation. And all I've done here is I've taken another 100-second period simply to show that the rate of reaction here is decreasing because NO2 increased by that much in this 100 seconds, but it only increased by that much in this 100 seconds. So you can see that the rate is falling. Okay, so that's that. We've finished now, and then we'll look now at the methods of measuring rate. This is it here, the methods of how you could measure rate in the lab